Okay, volumes of lines rotated around the x-axis. You can go both the x and the y. We're only going to focus on the x. This is how we do it. Okay, so the most basic one we have, the most basic function we have is a horizontal line. So y equals, in this case, y equals 3. This distance right here is 3 away from the x-axis. Okay, and we're talking about from 1 to 6, so this distance here is 5. Okay, so what we've done so far, what we've done previously is we've just found this area in here. And we know this area to be 3 times 5 or 15. Right, and that's a little bit of what's happening here, but we're not going to focus on that. If we rotated this line around the x-axis, it's hard to visualize, but imagine this is a string or something and we're just holding it tight, and then this shape right here is created, right? This shape right here. So if I'm rotating this thing around all the way through, then this shape's created. If we're talking about a horizontal line, y equals 3, then that shape is in fact a cylinder. So the x-axis is the center of our cylinder. This line is always 3 units away from the x-axis. And if we rotate it around, the three-dimensional shape we get is a cylinder. Okay? Now, real quick, this cylinder with a radius of 3, that's this radius right here, has an area of pi r squared, has a volume of pi r squared h, which in this case is pi 3 squared times 5. So this is our 5 and this is our 3, whatever, that's simple enough. But if we're thinking about this in the terms of a function, we can simply say, instead of 3, we could say f of x. And if we're talking about a variable function, right, a function that doesn't have this horizontal line here, all right, it's a curved function, then what we're talking about is the volume would be pi, as always, this distance, which is f of x squared. Well, this distance is no longer simply straight 3. It's a variable function, still times the 6. Okay, and this is a little bit confusing here, right? But if we're thinking about this as using integration, all right, then this would be pi on the outside, our integral from 1 to 7, in this case we're doing 1 to 7, doing this curve right here, of whatever the function is, squared, because whatever the function is in fact our radius. Whether we're at 7 and our radius is here, or whether we're in the middle and our radius is here, or wherever we happen to be, every f of x distance is in fact our radius. So this integral applies to this specific function, but the general formula, and it's really basic, we'll talk about the application in a minute, or the reasoning behind it in a minute. Pi, there's my r squared, and this is really our height. Our stacking up from a to b is really our height. We can think of it that way if we want. Okay? All right. So, where it looks like, what it looks like on a problem. All right? We're not going to do this one out. We're just going to talk about it. Then we'll do a couple out as examples. So the wording can be a little bit different for both of them, but generally speaking, it's find the volume of the object created, or I might say solid object, when the function, in this case f of x equals x squared plus 4, which is simply an upward-facing parabola with a y-intercept of 4, is rotated around the x-axis. Again, that's very important. We can do the y-axis as well. From x equals 2, that's right here, to x equals 5, that's right here. All right? So what we're talking about is rotating this curve around the x-axis. So we're rotating it around the x-axis, and it rotates, and it comes around. And this is a 3-dimensional figure, because we have this sliver right here. When I say sliver, I'm talking about a little disc. This is a disc. This first disc has a radius of 5 squared plus 4, because that's this distance. This distance right here is 5 squared plus 4, so it's 29, right? And this distance right here is 2 squared plus 4, or 8. And then all the way through here, it's whatever my x value is, therefore it is f of x. Now, if we're talking about this problem, just calculating the volume, just the basic formula is this: pi, this is my height, remember, okay, like I said, this can be thought of as our height even though it's a horizontal distance, right? Our function, x squared plus 4, is our radius wherever we happen to be. If we're at 2, then our radius is going to be 8. If we're at 5, our radius is going to be 29. Whatever the case may be, that radius is being squared. And then this is the formula: volume equals pi r squared. Well, here's my r, r squared h. Well, here's my r squared. This is my h, again, essentially, and that's my pi. So if I'm doing this on my calculator, I'm integrating this just like it is, and I'm probably going to leave the pi as 34 pi or 4.7 pi, or just leaving the pi by itself, unless I have to round it to a decimal, then I'll just multiply by pi. But I'm putting this function into my calculator. Before, when we were calculating the integral, we would only put the function. Well, now, the only change is we're encompassing this, and we're squaring the whole thing, and we're putting that function, and then we're evaluating from 2 to 5. Okay, so this is the basic formula. All right, so let's do a couple problems. You're going to have to, let's assume we're not going to have a calculator available to us. Okay, so we're going to have some idea what these graphs look like. Find the volume of the solid generated by revolving the region bounded by the graph y equals x, y equals 0, and x equals 4 about the x-axis. Like I said, we're going to be doing all of these about the x-axis. So, just draw a quick little xy axis. Now we need to understand what we're talking about with these things. Y equals x is a basic equation like that. Y equals x. So that's that. Y equals 0. This is my y-axis. This is my x-axis. Oh, okay. So that's my x-axis. I need to know that. I need to remember that. So this is the bottom boundary. Okay. X equals 4 is simply x equals 4. So again, find the volume of the solid generated by revolving the region bounded by the graphs y equals x, check. Y equals 0, check. This is y equals 0. And x equals 4, check, all about the x-axis. So this is the region. Now we can think of it in a couple different ways, but we're going to think of it in this way, that I'm going to create a disk here, and this disk has an area of pi r squared, but in this case, pi times 4 plugged in here. So I'm just going to say pi x squared. Now, this is x, but we know it to be 4, but it doesn't matter. It's anywhere around here is my function squared. Okay? And we're going from 0 to 4, because this is 0, because that's where they intersect. Okay? So this whole thing, when I'm rotating this, becomes the integral. We put our pi on the outside, O is in forever. Our range, our x range is 0 to 4. So our lower boundary is 0, our upper boundary is 4. This is, again, we can think of it as the height of this object. And then our radius is x, and we square that, and we get dx. And that's what we put. Forget in our calculator, we'd actually work this out. We'd go 1/3 x to the third power. Why don't you work that out real quick? Okay, so the answer comes out to 67.021 if we do it on our calculators. All right. Now, notice when we put this in our calculator, this is not going to look like our function. It's not going to look like this because we're squaring it. So when we put this in our calculator, it's going to look like this. And it's going to have a curve to it. It's going to look like x squared. And then when we calculate this region, this black region, or this red region right here, That's what you're going to be multiplying by pi. So that's whatever this is times pi. Okay? All right, next one. Boom. Okay. Find the volume of the solid generated by revolving the region bounded by the graphs y equals x squared, y equals 0, and x equals 2 about the x-axis. Again, we're doing x-axis. So, boom, boom. There's our x, there's our y. Y equals x squared. Simply there. Okay. Y equals 0. We did this last time. So y equals 4 is horizontal. Y equals 0 is this horizontal line. So we're good there. We could double it up just to make it a little darker if we want. So that's that. That's that. And x equals 2 is a vertical line. X equals 2. I don't need to label the rest of this whole thing. Like, this is not important to have all these different numbers. And this region is being rotated around. And by the way, it's going to look like that. When I rotate this thing around, it's going to look like that. It's going to look like a little pointed hat. And up here it looks like that. It's like that cone. But this has some curve to it. So this is going to look like this. All right. So when we rotate this around, again, to think of what's going on exactly, it's a little hard to wrap our head around. But let's do this two ways. Let's first think about the general formula, boom. And the general formula is pi from a to b of whatever function we have squared. Okay, that's our general formula, all right? Again, to understand exactly why, it's a little bit confusing, but let's not concern ourselves with that. All right, so if I'm applying this to this, then this becomes pi, as always. The integral, in this case, 0 to 2. My function is x squared, but I'm squaring that. Don't get all confused about that. So therefore, this becomes pi integral 0, boom, x to the 4th dx. And I'm going to do this just like before in my calculator, and I'll work it out, and I'll let you work that out. All right? Okay? So that's my true solution. All right? And it's simple enough for me to calculate. Okay, find the volume of the solid generated by revolving the region bounded by the graphs. Y equals e to the x. Y equals 0. Okay, sorry, interrupted by one of my boys. All right, so y equals e to the x, y equals 0, x equals -1, and x equals 1 about the x-axis. So I'm just going to draw this quickly because we're running out of time. There's our region, okay? There's our interval. So we go boom, we go pi, we go -1 to 1. Our radius, or our function, is this dx. And that becomes our volume, okay? And that's that. And we go e to the x squared. Whether you know the rules or not, or whether you have your, you can put it in your calculator just like that anyway. Okay, I'll let you do this one all by your lonesome. Find the volume of the solid generated by revolving the region bounded by the graphs. Y equals square root of 3 minus x. The x-axis, x equals -1 about the x-axis. All right.